The SoNIC framework offers a novel approach to safe social navigation by integrating adaptive conformal inference and constrained reinforcement learning. This methodology ensures navigation decisions are both safe and socially acceptable. It utilizes conformal inference to assess environmental uncertainty and reinforcement learning to optimize decisions based on safety and social constraints. The authors emphasize the importance of considering both safety and social norms, highlighting the limitations of existing approaches that prioritize one aspect over the other. The SoNIC framework's adaptive nature allows it to adjust to changing environments and social contexts, making it a promising solution for safe and socially aware navigation. This paper introduces a groundbreaking approach to social robot navigation, combining nonconformity scores from adaptive conformal inference, ACI, with constrained reinforcement learning, CRL. The authors propose a technique called spatial relaxation, which transforms collision rate constraints into cumulative intrusions, simplifying the optimization problem without compromising safety. They also present SoNIC, a method that integrates ACI and CRL to generate safe trajectories with minimal pedestrian path intrusions. The paper reviews related work in social robot navigation, planning under uncertainty, and safe reinforcement learning. It highlights the challenges of modeling dynamic human behavior and the potential of deep reinforcement learning, DRL, in addressing these challenges. The authors discuss previous trajectory planning methods under uncertainty, including optimization-based, search-based, and DRL-based planning approaches. In the context of safe reinforcement learning, the paper notes that incorporating safety constraints into DRL methods can help avoid dangerous conditions. It mentions various techniques such as state augmentation, adding safety layers or agents, and Lagrangian methods, with a focus on the ease of implementation and performance advantages of Lagrangian methods. The paper concludes by outlining the preliminary concepts necessary for understanding the proposed method, including adaptive conformal inference and its ability to quantify uncertainties in a model-agnostic manner. It emphasizes the advantages of ACI over traditional split conformal prediction, particularly in terms of dynamic parameter adjustment and exchangeability requirements. The SoNIC framework integrates human trajectory prediction, attention mechanisms, and constrained reinforcement learning to enable social navigation in crowded environments. It consists of human position estimation, robot feature extraction, trajectory prediction, and uncertainty quantification using adaptive conformal inference, ACI, and dynamically tuned adaptive conformal inference, DTACI. Uncertainty metrics are concatenated with predictions and fed into networks with attention mechanisms for human-human and human-robot interactions. The cost function is designed based on physical information and prediction uncertainty. The constrained reinforcement learning, CRL, agent uses a proximal policy optimization, PPO, Lagrangian approach, where the actor and reward critic share some layers, and the cost critic uses a separate network. The agent is updated using reward value loss, action loss, and cost value loss. The problem formulation involves predicting k future steps for each human's trajectory and formulating the task as a constrained Markov decision process, CMDP. The CRL agent generates actions to control the robot's moving speed based on observations of physical information, predicted human trajectories, and post-processed features. The goal is to obtain an optimal policy that maximizes rewards while adhering to constraints on costs. SoNIC introduces two mechanisms: ACI for quantifying prediction uncertainties and incorporating them into the state representation, and CRL for guiding the agent's behavior based on uncertainty quantification. The DTACI method is used to quantify prediction uncertainties, providing predefined coverage of prediction errors and adapting to distributional shifts in an online manner. The cumulative intrusions of the robot into other agents' spatial buffers are constrained, offering behavior-level guidance and addressing the issue of sparse feedback. The integration of uncertainty quantification into the decision-making process of RL agents for social navigation is discussed. This involves the concept of spatial relaxation, which allows for a more flexible approach to managing safety by tolerating minor intrusions within a controlled buffer zone. The buffer zone is designed as a combination of a circular area around the human's current position and an area generated by ACI around predicted positions. The cost function includes a term that penalizes intrusions into the buffer zone, and the reward function drives the ego robot to approach the goal while avoiding collisions. The optimization problem is formulated using Lagrange duality, transforming it into an unconstrained RL problem that maximizes a combined reward. Please provide the text you'd like me to refine, and I'll create a concise, technically accurate summary suitable for voiceover narration. I'll follow the guidelines you've outlined, ensuring the refined text maintains the essence of the original research while being optimized for audio presentation. The authors present the results of their experiments on in-distribution and out-of-distribution test scenarios for various navigation methods. In the in-distribution tests, SoNIC outperforms other methods in safety metrics and intrusion time rate, indicating it can generate safe and polite trajectories with minimal intrusions to pedestrians. Direct constraints on collision rates do not improve safety, as CRL does not offer advantages compared to RL. A qualitative analysis shows SoNIC chooses to move the robot out of crowds to prevent potential collisions, while crowd NAV++ decides to approach the goal directly, leading to an almost inevitable collision. In out-of-distribution scenarios mixed with 20% rushing humans, all methods perform worse, with a significant performance drop in RLBA-SED methods, implying rule-based methods can maintain a baseline but struggle in complex scenarios. In out-of-distribution scenarios, the authors test their robot navigation system, SoNIC, in crowded environments with humans exhibiting diverse behaviors. In the first scenario, humans rush towards the robot, and SoNIC with the GST predictor successfully navigates through uncertainty areas generated by the adaptive confidence interval, or ACI, and escapes to a safe area, as visualized in Figure 3c. Notably, SoNIC with the CV predictor demonstrates higher stability across different random seeds, likely due to its more stable performance in out-of-distribution conditions. In the second scenario, the authors modify the human agent's moving strategies from optimal reciprocal collision avoidance, or ORCA, to social force, or SF. The results show that all methods perform better than in in-distribution conditions, with SoNIC achieving almost perfect success rates, collision rates, and time to reach the goal when paired with both GST and CV predictors. This suggests that SoNIC adapts well to out-of-distribution conditions caused by different behavior models. Figure 3D illustrates a scenario where SoNIC with the GST predictor maintains a conservative distance from the crowds and successfully escapes. The authors also validate the effectiveness of ACI in covering actual prediction errors, visualizing the ACI errors of one human in Figure 4. The results demonstrate that ACI quickly adapts to the actual prediction error and achieves adequate coverage, ensuring that the uncertainty estimation is not too conservative. Finally, the authors deploy SoNIC on a real robot, an iRobot Create 3, and test it in scenarios with 58 humans walking in a 5.3 meters x 6.4 meters area, further demonstrating the system's robustness in real-world environments. In this paper, the authors introduce SoNIC, a novel algorithm for social navigation that combines affordance-based collision inference, ACI, with cost relaxation learning, CRL. This integration enhances the learning process of reinforcement learning agents by utilizing nonconformity scores generated by ACI. The spatial relaxation technique is also employed to increase the applicability of CRL in social navigation, providing richer cost feedback and facilitating convergence without compromising safety. SoNIC achieves state-of-the-art performance in both safety and adherence to social norms, demonstrating robustness to out-of-distribution scenarios. The authors plan to extend SoNIC to incorporate perception uncertainty and develop an end-to-end solution for social robot navigation, aiming to address navigation tasks in complex real-life environments.